Hey, Cyberspace, Nathan Wallace coming at you from home office. This is, I believe, really the first video as far as technical deep dive. And today's topic is on power system cyber assets. So what is a power system cyber asset? What really needs to protect it? What needs to be protected? What doesn't? So let's go ahead and get started. So today's grid power systems. We're really replacing these old electromechanical relays, and even then, there's still a lot of electromechanical relays out there, and we're replacing them with computers with intelligence. So this is an example network topology as far as systems at the grid edge. These distributed systems. So you may have a local HMI talking to some switch. This is the firewall. So incoming from the outside. Let's see if I can switch over to the pencil. So here, change the color as well. Let's do sky blue. So all the traffic is actually going to come in from here. So this is like your SCADA traffic is going to come in from here. So firewall, everything's kind of whitelisted. We have our local switch, so this creates the local area network. Or our LAN, and then the HMI human machine interface there at the substation or power plant, some protective relay, and then you could have the RTU remote terminal unit. So if you see, this is the solid green line is basically the TCP/IP based traffic, Ethernet based traffic, and then we have here's another Ethernet based relay. Ethernet communications based RTU, and then this is serial communications. So this could be vendor specific, this could be general, different protocols as far as, let's say, even Modbus. So that communicates with the RTU, and basically this RTU kind of acts as a protocol converter, even pass-through, so you can encapsulate some communication into Ethernet. So this RTU will serve that function. So, a lot of capabilities. This is what's happening, right? And we need it, as far as adding more intelligence. And I kind of joke with different colleagues at work. There's today's grid, today's power systems. There's not an electron floating on the grid, moving on the grid, whose fate, whose destiny wasn't controlled by a computer. So it's pretty neat to think about like that. Let's see. So keep on cruising. So two infrastructures, right? Today's grid, there's really two infrastructures. Let me clean that. Clear current page. There we go. So, the traditional grid, right? Generation, transmission. There's the physical aspects. Come down, and then we have our distribution system down here. So residential, commercial, and industrial. Well, now we've kind of overlaid it with this massive cyber infrastructure. So that's pretty much everything in blue as far as these blue spheres or ovals, and then the lines. So the blue ovals kind of represent computation, so computing, and then the arrows represent the communications back and forth. So we're just, putting it into, not only the computations into these individual systems, but now we have RTOs, ISOs, we have control centers, distribution operation centers. Now we're talking about this idea of virtual power plants to manage solar, distributed energy resources, for instance, to bring that power back to support, the rest of the grid. So a lot of capabilities. It's just, increased intelligence. And then this is a really cool, kind of eyesore, especially when you bring it up in a giant conference room. So this is the NIST, National Institute of Standards and Technology, Smart Grid Framework. So we have our different categories as far as domains, right, that really kind of make up the power grid or these power systems, at least in the U.S. So, we have our markets, so there's selling power back and forth, even between the different utilities. We have our operations, so that's the managing of all this stuff, energy management systems, wide area management systems, asset management, distribution ops, so distribution management systems, distribution SCADA, supervisory control and data acquisition. So we have that at the distribution system as well as the transmission system. And then we have also these service providers that are kind of, some are third party, some are outside the utility, and all these different domains, all these different blocks as far as functions that or domain gateway actors are, looking at the legend here, that now take part in the grid as far as the operations and maintenance of the grid. There's even the customer domain, premise networks, your smart meter, for instance, electric vehicles, a lot of IoT specific stuff that just kind of happens right here as far as at the customer, at the load level. And then, substation, local area networks, a lot of cool stuff happening there as far as distribution automation, substation automation, new protocols like 61850 that help just add more intelligence to the system. So this is what's happening as far as our industry right now. And so when you look at the assets, this is an example system topology. Up here, once again, following this 3-tier model, we have our generation. Voltage is stepped up. We have transmission. We're serving some industrial customer right here, for instance. And then it steps down again, or back down, and then we have our residential. So, looking at this, you may have at your transmission, you may have a tower that's doing microwave communication between your towers. For instance, a lot of people view that as air gap. Well, it's wireless, so it's not air gap. Or they, some vendors even sell the technology as creating a closed LAN, isolated network, and well, if it's wireless, is it really isolated? So if we look at some of the smart grid technology, we have AMI, automated metering infrastructure. Here's an example of a recloser that's actually controlled from an iPad. There's also an app for the iPhone right there. So battery storage as well, a lot of software that keeps those systems up and running reliably. Software that's on these battery storage systems, they control the flow of power. As well as this increased power electronics. So if you look at the individual sites, kind of these remote sites, so this is substation, power plant, you have your ESP, your electronic security perimeter, and anything within there. If someone brings it in, connects it, that's now part of the electronic security perimeter. And then, goes out through some external communications infrastructure, so we have all these different, you can have fiber, so OPGW, optical ground wire. So the transmission line here the ground wire would have fiber optic in the middle. So that allows you to communicate, kind of some cases create like a ring bus between your different substations. You can also use satellite. You can, some installations actually use the internet, to remotely communicate over via some VPN, for instance, as well as the microwave wireless here as shown on the bottom. And then, we have our control system LANs. So this is like your control center. Your SCADA, your operators, you have some DMZ or demilitarized network, and then some corporate LAN. So a lot of information all over the place. Some people joke as far as, the systems need to be isolated. And it's like, obviously they've never worked in the power system industry or power industry. If they think that these systems can be up and running, if you can maintain reliable systems without having that connectivity. So on this topic of assets, there's a lot of vendor confusion, sales pitches. So these are things that I've personally observed, and I get a good laugh out of them. So example one, we have these electromechanicals, and in some cases you still need to track how much power is moving, right? So you keep your relay there, and you install some some revenue meter. And this particular vendor was really using this as a sales pitch for their meter, saying, you don't have to worry about cybersecurity, the NERC-CIP requirements, the cybersecurity requirements, because this meter doesn't do control. It's just doing observing or monitoring as far as the power flow. And he was really pushing that to say, okay, this guy, you don't have to worry about any protective cybersecurity controls because there's no control, or protective measures because there's no control. But what happens if the values that are coming out of this meter, what happens if they're changed, altered, spoofed? The software on this meter is now changed or altered to where the SCADA operator, whenever he receives these values that are, basically coming from the meter to the RTU and then being sent up to the SCADA operator, What happens if they're changed? What happens if they're altered? So he can really, almost hack the operator into thinking that the grid is in one state when it's actually in another state. So that was a sales pitch I heard. Now I was really disappointed in this particular vendor when they made that statement. Example 2, here's another vendor. This was on their data sheet, basically on their cut sheet. Yeah, the solution is an install and forget it, hassle-free, 100% safe approach for SCADA communications. And, this is really the mentality as far as the hope, that we can just plug and play and then these systems can just stay without any maintenance as far as the software maintenance or the IED, intelligent electronic device maintenance. And that's not the case. These systems can become vulnerable over time. They have vulnerabilities that are discovered. So poodle, heartbleed, shell shock, those are some examples of vulnerabilities that we found inside of these assets over the years. So the question is, what needs to be protected? What devices need to be protected when it comes to the grid? So the way I look at this, it's really, let me change this back to black. So what needs to be protected? So the question is, in my opinion, as far as, in making this determination, it's what has computational, let me get back here, what has computational and or communications. So what has computational and or communications ability and is used to ensure the safe, reliable, and continuous. So what has computational and or communications ability and is used to ensure the safe, reliable, and continuous, and then you guessed it right, the 3 domains. So we have generation, and then we have transmission, and instead of distribution, I actually say delivery, because if you look at some power systems, they really don't have a distribution system. It may be just local or isolated. So this kind of encompasses that distribution. So what devices need to be protected? Well, what has computational and or communications ability and is used to ensure the safe, reliable, and continuous generation, transmission, and delivery of electrical energy. So safe, safe. Lockout, tagout, for instance. There's some installations that have that to where it's all in software. This ability to lock out and tag out a line. That way, if you have crews working on it, you can't close that in and energize the line while individuals are working on it. So safe, you have to maintain that level of safety. Reliability, so this is that voltage control, frequency control, reliable. And then continuous, when I expect it on, I expect it on. And then, like I said, generation, transmission, and distribution. All right, so let's keep on cruising. Clear the board here. Let's go back. Clear current page. So looking at these assets, these are examples here on the left as far as power system cyber assets. There's the laptop, computer, switch, media converter, firewall, radio, RTU, remote terminal unit, relay, meter, and PLC or programmable logic controller. So when you look at this, these are examples of different cyber assets, but when you take a closer look, it's not just the devices, right? So let me bring this back up. So cyber asset is really anything, like these programmable electronic devices. So all of these are examples of programmable electronic devices. But, if we look at it, we also now can divide this up into 3 different categories where we have the hardware, we have the software that's running on the hardware, and then we also have the data that's inside there. Let me fix my H up here. That's horrible. Huh? That's what happens when you're still getting used to this tablet. I'm actually just going to go ahead and redo that whole thing here. So let's say it's, like I said, it's the hardware, software, and data. So examples of the hardware, we have the I/O cards. We have the different, let's say, network cards that would also be added. So you can, you have I/O as far as input output, contacts, right? Different data being brought in, different wires, and then you have the network card. So that's like all your communications. Let's say if it's a 61850 module, a Modbus module, DMP3 module, etc. And then you also have basically the ICs or integrated circuits. So you think about this. You got your CPU, you have your RAM. And then other types of like physical ports, and this is really important because if this kind of gets into the supply chain debate as far as the integrated circuits. There was a good presentation, two actually good presentations. Schweitzer Engineering Lab and then ABB did a similar presentation at the IEEE Smart Grid cybersecurity workshop last year, and they went over basically the pains that they go through to make sure that the integrated circuits that they receive from the different vendors, wholesalers that they procure their chips from, to make sure they're not counterfeit, to make sure that malware is not installed on the chip. They actually had a cell phone a couple years ago that had malware in the chip or in the baseband processor. Kind of the CPU that interfaces with the cell towers, and if you sent a certain text message, it would actually open up the phone. So that was malware that was installed on the integrated circuit itself, as well as the I/O card. So this is important because you don't want your I/O cards. We go through all this pain as far as procuring the IED, the relay, the RTU itself from a reputable vendor, but then we go and purchase our I/O cards for that RTU on eBay because they're cheap, for instance. Well, that could introduce malware, that could introduce stuff into your system. And then you also have your software that's running. So this is kind of some of the let's say user apps. So something the operator would install. So this is the let's say EMS, HMI stuff, so energy management system software, human machine interface, even the FTP stuff, all the way out, right? So user apps, we also have let's say any kind of device apps that come on it. So we have protocol parsers, converters, etc. So let's just do converters. So this is some of the vendor software that may come on here to kind of convert the different protocols. So you have to make sure that stuff's secure. Let's see. We also have different libraries, APIs. So let's just say software libraries. And let's say and APIs. So if they're inheriting or if they're pulling in, some open source library, some open source tool to make their own kind of secret sauce, what vulnerabilities now does that introduce into the system, as well as the data that's actually in those devices. So, you think of this as, in the case of a relay, you can look at the settings and configuration files. So this is basically saying, okay, what's my impedance of my line? Where's my zones as far as my protection? If we're talking about a relay, what type of protocols are we converting? If in the instance of the RTU, or even what type of automation we're implementing at that substation. If it's, let's say, an automation controller or like a souped-up RTU. Let's see. Any type of stored values. So let's say logs. Sequence of event reports. Let's see, digital fault data, some DFR logs, and then things like, the trivial stuff like usernames, and then, hashes, like profile hashes, profile password hashes. So all this needs to be protected. Your settings and configuration file, you have to almost track, do the full chain of custody as it's moving hands, as it's exchanging hands before it gets installed on devices in the field. So a cyber asset, yes, it's the programmable logic electronic devices, like all of these over here, laptop, all the way down to the PLC, the programmable logic controller. And including the hardware, software, and data. All right, let's keep on cruising. Clear that page. Go to the next one. So once you've kind of identified all those devices that have that computational and or communications ability, you then need to come back and say, okay, well, how do you implement it? How do you implement the cybersecurity? And it's, the implementation challenge is, as far as the engineering standpoint, how do you maintain? And so if you look at all those assets that we just looked at, as far as, what is a power system cyber asset? So the challenge is, how do you maintain and this is the CIA triad, as far as the, InfoSec community. So how do you maintain the confidentiality, the integrity, and the integrity and availability. So the CIA triad, and the reason why we call it a CIA triad, you can kind of look at this as a little triangle. So CIA, and what's interesting when you kind of do this, and you when you're trying to do this implementation, you can almost say, okay, well, whenever I try to increase my confidentiality, so let's say encryption and all this other stuff, you're almost pulling away from these other two. So let's say if you're doing encryption, in some cases the integrity goes down, the availability goes down. This is why we really can't go in and do encryption across the board in SCADA systems, is because it causes increased latency. Well, that affects the availability. I need it right now. I need it at this very second. And then same thing, as you implement more integrity, you're kind of pulling away from the CA. And as you do availability, you're kind of pulling away from CI. So how to maintain, so this is, like I said, this is the implementation challenge, how to maintain confidentiality, integrity, and availability of power system cyber assets. While each protective measure, it must not impede. So this is really the challenge. It must not impede access and operations during legitimate activities. So you have to implement this stuff. You have to implement the confidentiality, integrity, and availability in such a way that it must not impede access and operations during legitimate activities, and it must be technically, economically, and operationally feasible. Right, so each protective measure that we implement that helps us achieve the CIA, the confidentiality, integrity, and availability, each one must not impede access and operations during legitimate activities and must be technically, economically, and operationally feasible. So these two things right here, these two items, let's come over here. These two items are actually defined and discussed in this standard right here. So this is IEEE standard C37.240, IEEE standard cybersecurity requirements for substation automation, protection, and control systems. So this is one of those things that really, I kind of not really get into debates with, but, as far as looking at to say, okay, is power system cybersecurity unique? So the challenges, I believe, are unique to only our industry, only the power system industry. So this is power system cyber assets. This is kind of how I look at it. Like I said, the key takeaway is definitely what needs to be protected. So this is it right here. What has computational and or communications ability and is used to ensure the safe, reliable, and continuous generation, transmission, and delivery of electrical energy. So this is it as far as the first kind of deep dive. If you have any questions, comments, feel free to comment below or shoot me an email. All right, thanks.